So today we're looking at our notes for section 4.4. We're going to really be using our calculators a lot during this section, and we're going to be evaluating logarithms with two specific bases, base 10 and base E, Euler's number. And then we're also going to talk about the change of base formula. All right, so the first base, logarithmic base that we use that quite often is base 10. And we use it so often, and it is so common that we just refer to it as the common log. So logarithms of base 10 are used quite a bit. They're used a lot in science and in mathematics. And so we use them so often that we could just leave it off and just write log of some argument x. And so without a base, everyone's going to agree that that means base 10. Okay, so let's look at some things here based some of these you could do without a calculator, like this first one you should be able to do without a calculator. But basically we're going to use a calculator to do these, and I'm going to show you using your standard calculator so that you all this is kind of the calculator that I think most of you have, so we'll be using it to sort of do most of this work. All right, so the first one, log base 10 of 1,000. Well, remember, the logarithm is equal to the value. You'd have to raise the base 2 to make it equal to the argument. So I think without using a calculator, everybody can see that that is 3. All right, now the next one we would have to use our calculator for, because 10 raised to a nice number is not 118. There's no sort of nice integer that you can use there. So what we would have to do is use our calculator. So see, there's a log button on your calculator. Notice that the second function for that log button, so it's log, L-O-G, so that just means base 10. And they don't put a base on it, so we know that it is base 10. And the second function of that same button is 10 raised to the x, which is the inverse function. Okay, so how do we do this? So we're going to hit the log button, and then we will type 118. It's really that simple. 118. And then, I don't know, you're probably not seeing this really well in the calculator, but I'm trying as best I can to get kind of the image to show up. And so that would be 2.07. All right, so 2.07. We know it should be a little bit more than 2 because 10 to the second power is 100. It's a little bit more than that. So 10.07 is fine for that. Okay. So then the next one, again, we're just going to really do the same thing. We're going to hit the log button, log, and then type in 0.005, and hit enter. And so this one, it makes sense that it's negative because this argument is less than 10. So we would have to raise 10 to the negative power in order to get it to be a fraction less than 1. And so this is negative 2.301 if we want to go out to the third decimal place if you want. Okay. Now, the next three are asking you to not use logarithms, but to do 10 to the certain power. So this, of course, is 10 to the third. That's just, without a calculator, we know that that is 1,000. But how do we do that in our calculator? So we'll hit the second function of the log. So we'll hit the second button. Let's clear this first. Second, and then the log, which is now 10 to the. Now you could also type in a 10 and then raise, the caret button here and raise to a certain value, but this is just a little bit faster. And so raise that to the third power, and then you can see that that is 1,000. All right, so same kind of thing here. 10, simply 10 raised to that. So we'll do clear that again. So we do second log button, so 10 raised to the, and this time we want 2.0719, and we just hit enter. All right, so that is 118, I would say roughly that equal, so approximately equal to. Now notice, not a coincidence that this value is kind of the same as this. This value is the same as this. So what we're having you do is inverses here. So could you guess what this one is based on this result? Hopefully you could. This one should be 0.005, but let's do that in our calculators. So I'm going to clear it again, clear, do second log, raise that to the negative 2.301, and hopefully we get something, yep, close to that. Not exactly, because, we're rounding a little bit. This wasn't the exact value either, but, we're rounding. So, okay. So that's just kind of getting you to use your calculators to deal with some logarithms. Let's look at an application that you see often in science, and that's the pH of a substance. And so in chemistry, pH is defined as this. pH is the negative logarithm of the concentration of hydronium ions in moles per liter. So pH is the measure of acidity or alkalinity of a substance. And, I'm sure you're comfortable or familiar with a pH of sometimes you use little strips and you put it in the substance, and it'll turn colors based on the acidity or the alkalinity. So typically round it to the nearest tenth. So let's look. Find the pH of a solution with the hydronium ion concentration of this. All right, so that is this value in here. So we're looking for the pH. Usually pH is written with a small p, capital H. And so that is equal to negative common log, because notice there's no base there, so it's base 10 of, and then 6.8 times 10 to the negative 8. All right, and so really that's just calculator work. You plug that right in, and you should get from your calculator, you'll get something like 7.16749. Of course, we'll round, so we're going to do an approximately equal to, and we round to the nearest tenth, so a pH of 7.2. And again, that's just, you're just typing that right into your calculator. Let's just make sure everyone's comfortable with how to do that. So we're going to clear it again, and we're going to do logarithm. Well, actually, let's hit the negative first. So negative, and then logarithm. And then we do 6.8 times, and then we want to do 10 raised to the, you suppose you could hit the second inverse function of the log of negative 8. So raised to the negative 8, and then close that parentheses, hit enter, and you get our value that we got, okay? And of course, we, for pH, round to the nearest tenth. All right, so 7.2 would be our answer for that one. Now we're asked to do in the reverse now. Find the hydronium ion concentration of a solution with a pH of 4.3. So now we have 4.3 is equal to the natural log, negative natural log of the hydronium ion concentration. Okay, so we want to solve for this time. And so I think what we want to first do is, well, first of all, we probably move the negative over. And now let's convert that to an exponential. And so if we do that, we say the base, which we know is 10, even though it's not there, 10 raised to the negative 4.3 is equal to the hydronium ion concentration. So again, this would just be something we do in our calculators. We take and do the second log button, clear first. So the second log, that's 10 raised to the, and we want negative 4.3. And that is equal to 0.00005. We could certainly write that as an exponential to scientific notation. So we could say that's 5 times, I guess, and it would be would be 0, 0, 1, 1. So 5, maybe 5.01. We're moving the decimal place over 1, 2, 3, 4, 5 times 10 to the negative fifth. And that would be moles per liter, I guess, would be what the units would be on that. Okay. So scientific notation, and you could certainly leave it like this if you wanted, but probably makes more sense to put it into scientific notation. Okay. Another application for the common log is decibels. So you probably have heard of decibels. It's some kind of indication as to the loudness of a noise. And so certain things you can only, there's a big issue in Montclair with leaf blowers and people complaining that they're too loud. Gas engine powered leaf blowers tend to be very loud. And so you can see, like, here's a gas lawnmower at 1 meter. It's pretty high decibels. What a jet flying over is, and so on, so forth and so on. Okay, so 4 decibels. It's a little confusing, but it's the intensity or the ratio of the intensities of a sound, I, over some threshold, really quiet sound. So we first assign an intensity I sub 0, initial intensity of sound, to a very faint threshold of sound. So that would be something you could barely hear. If a particular sound has an intensity I, so that's the sound we're interested in, then the decibel rating D of this louder sound is given by this. So it's a ratio of the intensity of the sound we're interested in, of that ratio of the intensity of the sound over the threshold sound. Okay, so find the decibel rating of a sound that's 10,000 times higher than just the threshold sound that you can just barely hear. All right, so we're looking for D, and it's 10 times log, common log again, because there's no base, so it's common log or base 10. And then the ratio, if the intensity of the sound that we're interested in is 10,000 times the initial sound, then we'd say it's 10,000 times I sub 0 over I sub 0. So of course the I sub 0s would cancel, and just leaving us with 10,000. And so this is just something we would plug right into our calculators. So let's clear it. And so it's 10 times the log of 10,000. All right. And so that is just 40, which makes sense because we know this, right, that amount, log base 10 of 10,000 should really just be 4. And so that's 4 times the 10 that's out in front. So it's not surprising that this is equal to 40. So 40 decibels, it would be somewhere in the range of a dishwasher running in the next room, or quiet library, something like that. Okay, so not really that loud. It sounds like it would be really loud because it's 10,000 times the intensity of a threshold, but it's not really that loud. Okay, let's move on now to the second page of the notes. Now this is taking us to the second type of base that we're interested in, and this is base E, or this is Euler's number. And so we can find that if we take natural log, you have a button in your calculator, ln, that's the natural log. Let me clear this one. And so you can hit that and you'll do ln, or the natural log of a certain value. If I hit the second function, if I wanted to know what E is equal to, I can just do this and raise it to the 1 power, and you can see what that's the E, or Euler's number. Okay, so it's 2.7182818, so on. All right, so we often use, and we've already seen some examples of the E. We used it in the compounding continuous and population growth formulas, that kind of thing, growth and decay. We'll see this again more in later sections of this chapter, but we see this a lot in science. And so we use it so much that we don't say the log base e of something, we'll say the natural log. Some people say, well, why it seems like it should be the other way around. It should be natural log, it should be NL, not LN. But first and foremost, it's a log, but it's the natural log. So that's why it's LN. Okay, so let's look at some examples. Again, this first one, like we saw last time. So this one, don't really need a calculator for. The natural log of e. Remember, this could be the log base e of e, and that's e, the argument is raised to the 2 power. So using our rules for logarithms, we know that this is equal to 2. Now we could see that if we look at our calculators, and we did this in our calculators. Let's clear this. So we do the natural log. So the natural log, this time we want e. So I'm going to do second natural log, which is the e raised to the x power. So second log gives me the natural log of e raised to the second power. And you can see that when I hit the enter button, that's just equal to 2, which makes sense because we don't write it as log base e of e. We write it as the natural log of e, but we know that these sort of cancel each other out and just give us 2. That goes according to our logarithmic formulas that we got, the very first rules we got when we were doing logarithms. All right, next one. Again, you're just plugging this right into the calculator. So we're going to do the natural log, and then of 122, and we hit enter, and that gives us something like 4.804. Okay. Again, that's just strict calculator work there. All right. Now let's look at the next one. So the natural log of 0.05, you're just plugging that straight into your calculator again. So we do natural log of 0.05, natural log of 0.05, and hit enter. We get negative 2.99, okay. Again, just plugging those straight into your calculator. What would this one be? E raised to the natural log base e of e. What would that be equal to? Again, that's just using our rules that we learned before. That should be equal to, when these are the same, it's just equal to the base. The exponent on that e. So we know that that's just going to be equal to 2. Now we could test that out by plugging into our calculator. So let's try that. Let's do the second natural log. So that's e raised to the, this time we'll say natural log of, and then we want to do the e button again, and then that's squared. So the e raised to the natural log of e squared. And so now let's just hit enter, and you'll see, oh, that's not equal to 2. What is going on there? E, oh, no, sorry. That's not the base. Sorry, there's an E in there. So yes, oh no, I'm totally wrong on that. Sorry. Okay, so, sorry, it's E raised to the log base E of e to the 2, right? So this is all equal to e to the 2. That's the value I got. So it's 7.389. And so let's try that out. So what is e to the second? Let's verify that that works. Let's clear that. So we do, to get to my e, I'm going to do the natural log. So e raised to the second power. And sure enough, that's our value. Sorry, I was treating this as my base. That's not my base. That's the argument. E is the base. So e raised to the log base e, or the natural log, is just equal to the argument. So yeah, this is just equal to e squared. Not 2. Okay, next one. Again, it's just calculator work. So I'm going to take E and raise it to that power. Notice that's the same value as this. So we're doing sort of reverses here. All right. Oh, and you know what? Now that I look back at this, I think I did the same thing here. Did I do the same thing here? Log base E of E squared. No, that's right. That should be 2. Yeah, because that exponent can come down in front. Natural log of 2. So this is correct. I was just assuming this was the reverse. That's why I said that was 2. Okay, so this one, we should see that this is probably equal to 122, or approximately. But let's go ahead and check it out. So we do, let's clear it, and we do second natural log, which gives us our E raised to the, and we want 4.804, and we should get something close to 122. And we get 121.99. So yeah, approximately. Again, this was not an exact number here. We rounded here. So of course we're going to get a little bit of round off error. And then the same kind of thing, we would expect this to be the inverse of this. We'd expect this to be something like 0.05. Let's see what happens when we put that one in. So we do second natural log, so we get our E raised to the, and it's negative 2.996. And so sure enough, we get 0.04998. So yeah, it's approximately the same. Okay. Depending on what you round to, you get very similar answers. Okay. So let's look at this formula here. This formula is just the E in general, and the natural log is often used for trying to date old things, like we'll see with growth and decay, the age of fossils and those kinds of things. But here, geologists sometimes measure the age of rocks, T in years, by measuring the number of argon-40 atoms, A, and the potassium-40 atoms, K, present in the rock sample. So really, we're not measuring the number of atoms, but the ratio is really what we're interested in here. And so how old, so here's this complicated formula, but how old is a rock sample when the A and the K are equal? So when the number of argon and the number of potassium-40 atoms are equal, what is the age of the rock? So we have T is equal to, and it's 1.26, 1.26 times 10 to the 9, all right, and then times the natural log of, and then this ratio is going to be 1, so this is just 1 point, oh no, that's 8, so that's going to be 9.33 over the natural log of 2. All right, so just be careful with plugging all that into your calculator. It's a little tricky, but after you're all said and done, you should get something like 4,059,565,122. So how old is it? Well, it's approximately 4 billion years old. Okay, so 4 billion years or so. Probably can't, it's probably, that formula is not accurate to like, oh, it was a Tuesday when this rock was formed. You can't be that accurate with those formulas probably. All right, and so now we're kind of looking at reverse, they're using the same kind of thing, but now they're giving us the ratio. So the ratio is closer to 1/3 rather than 1. So the same thing. We kind of simply just put in the same thing, 1.26 times 10 to the 9th, and then the natural log, 1 plus 8.33 times the ratio was 0.325, and then over the natural log of 2. Okay, so again, that one's a little bit trickier to plug in, but once you plug all that in, you get something like 2,000,000,000 2,381,840,253. Of course, you can't really, probably say it's that exact. So we say 2.4 billion years, something like that. Okay. And of course, we're just going to round. So we say approximately equal to 2.4 billion years is what you should get on that one. Okay. All right. So that's our two bases that we use a lot. And now what we want to talk about is the change of base formula. All right. Now the calculators do a good job of doing base 10, common log, and base E, the natural log. But your calculators, for the most part, won't do any other bases. Now, some of the more complicated calculators will these days do other bases, but we're going to assume that you're not using those because we only allow certain calculators. So this formula is going to be extremely helpful if you're not allowed to use any more complicated calculators than the ones we allow. And so what it is you have logarithm of some base A of the argument x. You can change that into, you can pick whatever base you want. Usually we use for base B here, we use 10, or we use E because our calculators will do that. And then you see the argument is the argument upstairs. The original base is the argument downstairs. So let's do an example. Let's change our base to 10 so that we can do that in our calculator. So first of all, log base 4 of 64. I picked these numbers specifically because we all know that log base 4 of 64 is 3, but let's change the base to 10 and see if we get that same answer as just a check to see that indeed this formula works. So using the formula, and we're going to use base 10, we're going to change this to log base 10, and I'm going to emphasize it by just putting it in, although you don't need to, of the original argument 64 divided by log, again, base 10 of the original base of the log, so 4. Okay, so this is something we would just simply do in our calculators. So let's see how we would do that. We're going to do this time we're going to do common log. Oh, I need to turn on my calculator here and clear it. So we're going to do the common log, so just log, and then of 64. I need to close that parentheses, so I'm closing the argument on that log. Now hit divide, and now hit log again. And then now we want to do log of 4. And I don't really have to close that parentheses, it'll close it for me, but let me just do it anyway, and hit enter. And sure enough, you get 3. So the calculator will gives us 3, which we already knew because log base 4 of 64 is 3. But using our change of base, you see it works the same. All right, so try this one then. And again, we're going to write it as, and this time I'm just going to say common log. I'm not going to write the base in. The common log of 17 divided by the common log of the original base 2. All right, and so again, we just plug those right into our calculator. We do log of 17. Got to make sure we close that argument and divide by log of 2. All right, and so that is 4.087, something like that. And again, it's going to be an approximation. If you want to do a squiggly equal sign, that's fine. But these are, once you start using your calculator, you're generally going to have approximations. Here, it was kind of a weird case. That was an exact value. These are not going to be exact values. So we do some sort of approximations with that. All right, and then the last one. Again, we can do log base 10 of 0.1 divided by log base 10 of 2. Okay, and let's do that in our calculators. So we do common log, and again, you could do natural log as well. Maybe on this one, I'll do them both ways. So log of 0.1, of course, we know what that is equal to. Log base 10 that would be a -1, right? Because 10 raised to the -1 is 1 over 10, which is 0.5. So we could have kind of done that one without using our calculators, but divided by log of 2, and so we get something like negative, and it makes sense that it's negative because this is a little smaller than the base, so it makes sense that it's negative 3.32. Let's round it to 2. All right. All right. Now let's go ahead and do this one with the natural log as well. So the natural log of 0.1. Now that one we couldn't really do without a calculator, and the natural log of 2. And let's just confirm, it doesn't matter what base I change it to, my calculator will do either one. So natural log of 0.1, and then close that parentheses, divide by the natural log of 2. And so that gives me, again, that same exact value. It doesn't matter what base I change it to, it's going to be the same value. Okay, no reason why we would do base 10 over base E. Just generally we'll just use base 10, although it doesn't really matter. Okay, so your homework is down here. This is due next class.